Hey everybody, I hope you all are doing great. So I was going through some researches recently, and I came across this one research which stated that, it takes roughly 250 milliseconds for you to click a red button. And what was very interesting in that research was that if you click that some red button, like it takes 250 milliseconds, and someone in this world, right, some person in this world is going to smile due to your red click, right? So I don't know what they were talking about. Let us get right with the continue with the question itself. Already we are doing good in the playlist itself. Let us not get distracted by these researches. Let's try to focus the next question, which is coin change 2. Now in this problem, you are given an integer array coins representing coins of different denominations and an integer amount representing the total amount of total money, right? And like it is pretty similar to the last question itself, in which we did this same kind of problem. Return the number of combinations that make up that amount. This time you have to return the number of combinations. You don't have to return the minimum number of coins required. You have to return the number of combinations that make up that amount. Okay, if that amount of money cannot be made up by any combinations, return 0. You may assume that you have infinite kind of each coin. The answer is guaranteed and it is in the integer range only. Let us look at the test case and then try to understand that what do they actually mean by combination, and let's just try to see some combinations for this first test case. So let's say these are the coins we are having, and we have to make a sum of, let's say we have to make an amount of 5. Okay, these are all the coin denominations I'm having a coin of 1 rupee, of 2 rupees, and a 5 rupees. All right, and I have to make a sum of 5, total sum of 5. Let us try to see some combinations, right? And it is given the problem itself that I'm having infinite supply to these coins. This means that I can choose a single coin as many times I want. Okay, so let us try to get 5. I can of course take this thing. I'll choose 1 5 times. That will be summing up to 5 itself. Definitely 5 coins of 1, right? Second type of thing is I can choose like this. I'll choose a coin of 2, I'll choose a coin of 1, I'll choose a coin of 2. This is also one of the options. This is summing up to 5 itself. I'll choose a single coin of 5 itself, and this is definitely making the sum of 5 itself. And yes, these are the options I'm having. One more option, which is that I'll make the sum of this. I'll choose two ones, and then what I'll do, I'll simply choose, let's say, a 2 and another 1. So that is also making 5, right? Definitely. Let us try to see some other kind of, is there any other possible test case? Let's say I'll choose 3 ones and then I'll choose a 2. So this is also making a 5, right? So I'm getting 5 ways total. Let's see in the problem. They are getting 4 ways. Okay. Okay. They're getting 4 ways and I'm getting 5 ways. All right. So what am I doing wrong? Right. This is the case, right, which we are getting confused in, right? Now, I am definitely wrong here. I am definitely wrong here. Why? Why? They are asking us for combinations. Combinations. What is a combination? Here, A, B, C and A, C, B. These are permutations of same characters. Permutations mean that, you know, you can say order matters, right? The things which are there, order matters. ABC is different from ACB, but when we are talking about combinations, order does not matter. ABC is the same combination as ACB, right? Choosing A, B and C, here also I'm choosing these three things only, definitely in a different order, but I'm choosing these three things only. So what is a combination? It is this only. That order doesn't matter. Can you see this test case which I've created? Here you can definitely see that you can see that I am choosing 3 ones and a single 2. Here also I'm choosing what? 3 ones and a single 2. This is the same combination, yes or no? This means that I'm counting the same thing again and again. I can delete one of the things, and these are now my total combinations to create this amount of 5. Is this clear to everybody that what do I mean by combination? I'm not talking about the permutations. I'm talking about the combinations. Order does not matter. You have to tell me in how many like combinations you can make this total sum possible, and this is the problem. Definitely we have already seen what is a wrong test case, what we don't have to do, and we do understand that what we have to do. Let us now try to look at some kind of solution. Let's try to come at some solution for this particular problem. Let's try to derive an approach, and one may think in such a way that I'll choose first coin, then I'll choose second coin, then I'll choose third coin, then I'll move forward. But let's try to do that itself. So let's say I'm having amount of 5 here, right? I'm trying just the same thing we did in the previous question. I am trying out 5 right now. And if I'm trying out, like if this amount is 5, let's say as the first coin I'll choose 1, or let's say as the first coin I'll choose 2, or let's say as the first coin I'll choose 5. The sum I'll be left with is what? The sum I'll be left with is 5 minus 1, which is 4. The sum I'll be left here is 3. Sum I am here is 0. Okay. Let's say this kind of case, if I can choose 1 as the second coin, 2 as the second coin, or I can choose 5 as the second coin. So if I choose 1 as the second coin, definitely 3 is remaining. 2 as the second coin, 2 is remaining. 5 as the second coin, you can say minus 1 is remaining, right? All right. Let's look at this 3 as well. I want to tell you that why this approach is wrong, right? Why choosing every single coin at every possible step is wrong. Let us look at this. Full focus के साथ देखना है देखो. So 3, if I choose 1 as the next coin, 2, or I can say 5. Here I'll be making a sum of what? Here I'll be making a sum of 2. Here I'll be making a sum of, here I'll be making sum of what? Here I'll be making a sum of 1. Here I'll be making a sum of, you can say definitely a negative sum, minus 2 I'll be making. Okay. I'll pause here for a moment, and can you see the problem? Can you see that what is wrong? I have to report the number of combinations, right? Can I say 2 3 and 3 2 are the same combinations? Yes, definitely I can say that, right? They are definitely different permutations, but they are same combination, right? Look at this test case, what I'm talking here. So I can choose, let's say I'll choose 1 as the first coin. I'll choose 2 as the second coin. So this is what? 1 2. I am getting to a sum of 2. I've got 1 2. Let's say I'll choose 2 as the first coin and I'll choose 1 as the second coin. I'm again getting this 2. So 2 1 is also there. So can you see this kind of approach is trying to place every possible coin as the first, second, or third, or fourth, or fifth coin, right? And this is wrong. This will give you permutations, right? You don't have to try every coin at every step. This will ensure that you are going over the permutations, right? I only want combinations. Let us now look at how we are going to look at combinations, how we can possibly solve this case of combinations instead of getting permutations. So before actually discussing the code and drawing the recursion tree, let us try to differentiate between combinations and permutations. A permutation can be defined as order of some people, right? 3 1 2 4. Both of these things are different. Both of these are combinations, permutations, right? So these are permutations because different permutations. Of course you can say that it is permutation 1, permutation 2. But when we are talking about combinations, can you see something? 2 1 1 2 1 and 1 1 1 2 2. Can I simply say that these are the same combinations? These are the same combinations. These are the same combinations. Same combinations. These are also what? They are the same combination. They are only single combinations. Even though their order is different, but order doesn't matter in combination, my friend. This I'm repeating again and again. And I'm just doing that for example, if someone do not have a maths background, they understand that what is a permutation, what is a combination, right? Here I'll treat them differently. Here I'll treat them same. So can I derive a definition of combination out of it? This is a very important point. Can I derive a definition of combination? Can I say this combination, anything which is having 3 ones and 2 twos is the same combination? Can I say that? Anything which is having 3 ones and 2 twos is the same combination. This is also having 3 ones and 2 twos is the same combination. Definitely I can say that. I'll use this definition to move forward in the question to solve the case of combination itself. I am saying that anyone I want to treat as combination, I'll just treat them in terms of their count of elements. Is this clear to everybody? Yes or no? So let's move and let's try to derive a recursion kind of solution for this problem. So one thing is for sure, that at every stage I cannot choose any different coin. What I'll do here, recursion is a little bit typical. Look at this closely. I'll first say that I want to try the 0th coin only, and the remaining amount is 5. Is this clear? This is the index of the coin I am currently on, and this is the amount which is remaining. Is this clear to everybody? Look at this. Now 0th coin is having 2 options. This coin will be having 2 options. I'll try to create some this kind of combinations, right? So what I'm trying to do, So I'll try to create this kind of combination that if ones are done na, I'll not be choosing another one in the future, right? For example, if I've used these three coins as, like, I've used first three coins as ones, I'll not be using ones anymore in the future because I've switched to two, right? I'm doing something like this. Full focus, it will be clear, don't worry. Look at this particular case here. These are the two calls I'll be making. First call will be if I am staying on one, and the second call will be move from one and never look back on one. Here, look at this thing, that why we are getting permutations 1 2 1. Yeah, this is a permutation. These both are different permutations. Why? Because this place you decided to choose two, and in the future you again decided to choose one. This is getting wrong, right? This is wrong because at every stage you're trying to choose an element which you have already moved on from. So to ensure that we are going over a combination, whenever I'll move from an element to a next element, to a next coin, I'll not be looking back, looking at the previous coin back again. So the first choice is if I stay and I use the 0th coin, and if I move to the next coin and I never look back on the 0th coin, this will ensure that I'm not getting any permutations. Now, if I'm staying on this coin, definitely 0 will be the coin itself. It will be 0 only because I'm staying on this coin, the 0th index, 0 1 2. But tell me one thing, I'll color them with different colors, 0 and 5. Tell me one thing, if I'm staying on this coin and I've used this coin, the remaining amount will be 4. Is this clear to everybody? I'm using the same coin and I'm staying on that same coin. So I'm, like, index stays on 0 and this 4 I've chosen. Like, this is the remaining sum after choosing coin 0th coin at the 0th index. Okay. If I move from this particular coin, I'll go to the next index, but I'll not alter the amount itself because I have moved to the next coin. From this stage onwards, I'll try to choose this coin. Right. Now, again, we are having two options from here. Either I can do what? Either I can stay or I can move. If I stay on this coin and I use this coin number 0, 0th index, so I'll stay on 0 and the remaining sum will be 3. If I move to the next coin, I'll be 1 with a 4. Okay, look at this 0, 3. Here if I go and if I stay, so if I stay, 0, 2 will be remaining. I've used this coin again. If I move to the next coin for the future, so 1, 3. Remaining sum, there is no effect. I'm just switching the coin. This is ensuring that I'll not be looking at the 0th coin again. This will always get incremented. Full focus ke saath dekho. We are having two calls from here, and if I am having two calls from here, what I'll do simply, if I am staying on this coin, so 0, 1, and if I move to the next coin, 1, 2. This first parameter is always index and second parameter is always amount. This you have to keep in mind. Let's look at this again. So here also I'll be making two calls. If I stay on the same coin, 0 is the remaining sum. If I move to the next coin, 1, 1 is the remaining sum. This is somewhat an interesting case. Full focus. So the remaining sum has become 0. This means that this path is choosing what? This path is choosing 1, 1, 1, 1, 1. 5 ones. So whenever I come to a 0, I'll do what? Whenever I come to a 0, when the remaining sum becomes 0, I'll return a 1, that I finally have found a way to create the sum 0, to reduce the sum to 0 itself. Is this clear? The original sum was 5. I have found a way, because the sum has become 0. I found a way to make this sum 0, which means that I have found a way to achieve this target. I'll return 1, that one way is found. Okay, 0, 1, if we move to the next coin. Yeah, this is also having two options. If we are, of course, you can see this will never give me a good answer, because all these people are greater than 1. Yeah, how can they possibly give me the sum which is equal to 1? They will always give me a sum greater than 1, right? So it will definitely call for the people. So it will call for what? If I use this coin, 1th coin, 1 will be the coin itself, because I'm staying on this coin, and the remaining sum will be what? It is 1 minus 2, which is minus 1. This is a negative sum. Negative sum means that no, not possible, and there is no way to reach target from this particular thing. So return 0 from here. Is this clear to everybody? Now if we move to the next coin from this index, what I'll simply say, that coin number will be incremented, right? So it becomes 2. but the sum will remain the same. It will be 1 only, right? And of course, what we'll do here, if we choose the second coin and if we move to the next coin, if we choose the second coin, I'll stay on the second coin, try to use as much as possible, right? We are creating this kind of thing, something, right? I'm trying to stay on a particular coin and I do not move to the next coin until I've done exploring that coin, right? So if I again stay on this coin number 2, number will remain the same, but remaining sum will become -4. It is negative. I'll return 0. I'll increase the pace a little bit. Now 2 comma 1, 2 comma 1. If I move to the next coin, I'll be standing on 3 with the 1. 3 is definitely out of bounds, so I'll return 0 from here as well, because there is no more coin left and the sum is still remaining, which is positive. This has got 0 ways. 0 plus 0, how many ways we can achieve a sum of 1 using all these coins? It is 0. So I'll return 0 to this as well. Now look at this case. How much sum can we achieve of 1 from all these people? This particular case was from the 2th index. This particular case is from the 1th index. I will definitely return the sum of these two things. I'll return 0. Right. 1 plus 0. I'll return the sum, because there is a way to create. If I'm having only sum 1, if that is the only sum I want to achieve, using all these elements after all the elements after or on the 0th element, I can definitely choose a single way. There is a single way to create one, which is just choose this one. So I'll return the sum of both these values. I'll return a 1 from here itself. 0 comma 2. We are moving to the next coin. If we are moving to the next coin, this is having two choices, that we can stay or we can move. If we stay on the same coin, we use the same coin, I'll be on the same coin. Remaining sum will be this sum minus this 1th coin, which is 0. Okay, sum has suddenly become 0. This means I've found a way to achieve that sum. So, and what is that way? 1 1 1 1 2. Can you definitely see? I think, okay, 1 1 1, and I'm not choosing any coin here. I'm choosing a coin here, which is 2. So this means that I found a way to achieve that particular sum. Okay, so I'll return a 1 from here, that there is a way to get a 0. Okay, if I move to the next coin from this state, definitely index number 2 and remaining sum is 2. Can I possibly make, you can say, that much sum? Only a sum of 2 using all these coins. The coins are more than the sum. I can never make, right? So I'll make 2 calls. I can get included or I can move to the next coin. If I get included, the coin number will remain the same, but the sum, remaining sum, will be -3. It is a negative sum, my friend. Return 0. 2 comma 2. I'm moving to the next coin. No more coins left and positive sum is remaining, so return 0 from here as well. This is the kind of recursion tree we are drawing. Don't worry, the only time it takes in DP questions to get the recursion itself. If you have got the recursive approach, the problem you can definitely see after we code recursion, the video becomes very shorter, right? And to be honest, I am focusing more that you understand the recursion itself, right? And once you understand it, I'm not caring about how short or long the videos are. The whole focus is on making some quality content for you, so that a person who has not understood till here might understand the thing here itself. Is this clear? So 0 and 0, there is no way. So 0 plus 0, I'll return 0 itself. There is no way. 1 plus 0, there is a way. If look at this, I'll again explain the meaning of what is this. 1 comma 2 we are having. 1 comma 2 means that from all the coins after 1th index, are you able to make a sum of 2? And in how many combinations can you make it? Definitely there is only one way. Just select this 2 and you'll be making a sum of 2. And this is how what we are returning. Whatever possibilities I'm getting, I'll simply return the sum of them. I'll be returning how many ways I can make 2 from this 1th index onwards. I hope this is clear to everybody from this index itself. Now 0 comma 2, how many ways are there to make a sum of 2 from all these people? 1 plus 1 I can say, and I can also say a 2. These are 2 ways. You can see from here I'm choosing a 2. This is a single way, and from here I'm choosing 1 plus 1, right? This 1 is getting from, we are getting from this, right? So I'll 1 plus 1, I'll return 2, that there are 2 ways to make a, you can say, 2 here from 0th index. Okay, 0 comma 3, I want to make a sum of 3, but I am not starting from the 1th index itself. I am switching 0th index, I am switching the index itself, and here I'll be calling for what? Here I'll be calling for, I'll just make it a little bit shorter. I need some space. So here I'll call for, if I stay on this index, if I move to the next index, you can definitely see if I stay on the same index, 1 comma 3, right? Remaining sum will be 1 comma what? 1 comma what? the remaining sum will be 1 comma, I'm choosing this particular coin, second coin, 1 comma. So second coin I'm choosing, remaining sum is 1. So can you observe one thing? Can you observe this thing? Overlapping substructure, my friend. We are calling this thing again. The things are getting overlapped. Is this clear? This always returns a 0, right? There is no way to create a sum of 1 using all these elements. Definitely. Yeah. So from here, I'll return a 0. Definitely. Using memoization, I'll say that I'll return a 0 from here. And you can see definitely, if I move to the next corner here, it will be 2 comma 3. Have we already covered 2 comma 3 before? I don't think we have. Okay, let's try to iterate over it. If 2 comma 3 participates, the sum it will make is 2, and you can definitely say 3 minus 5, which is minus 2, which is definitely what? A negative number. I'll return a 0 from here. And if I move to the next coin, definitely I'll be out of bounds. So 3 comma, whatever the sum is remaining, third index is not there. So I'll simply return a 0 from here as well. I hope recursion solution is clear to everybody. I'm trying to go as deep as possible. If it is clear, you can definitely move to the recursion code itself. That's why I've kept those marker in the videos. So don't worry. If anybody has not understood, I am there with you. I'll be iterating no matter what. So I'll return what? Here 2 comma 3 from 2 comma 3. Are there any ways? No. 0 plus 0, I'll simply return a 0 from here. I'm returning a 0 from here. 0 plus 0, I'll return a 0 from here. 2 plus 0, how many ways are there to make a sum of 3 from this index onwards? 1 plus 1 plus 1, and I can say 2 plus 1. These are the only two ways. Yes, my friend, definitely. So I'll simply return what? I'll simply return this 2 here itself, and this 2 will get returned. 0 comma 4. I'm moving to the next index. Can I make a sum of 1 comma 4? Yes. I'll do this iteration one more time and then we'll wind up. So I'm standing on index 1, and from index 1, if I choose this particular, or if I move to the next coin, if I choose this 1th index, so the remaining sum is 2 comma 2. Right, I'm okay, 1 comma 2, sorry, because 1 is the coin we are standing on and 2 is what I want to make a sum of. And can you see one thing? 1 comma 2 is already repeating itself. 1 comma 2 is already repeating itself, so it always returns a 1. I don't have to do these calls. This is what optimization is. So I'll return what? Whatever answer 1, the combination of like this 1 comma 2 returns now, what these parameters 1 comma 2 return, this will always return the same result. So I'll return 1 only. This is what we have learned in DP. So if we move to the next coin, I'll be standing on, you can say 2 comma 4. If 2 comma 4 stays, or we move to the next coin, if we stay on the same coin, I'll be standing on 2 comma minus 1. Yeah, 4 minus 5 is minus 1. Negative sum returns a 0. And if we move to the next coin, 3 comma 4, 3 is out of bounds, definitely out of bounds, also return a 0. 0 plus 0 returns a 0. How many ways are you able to make a sum of 4 from 1th coin onwards? How many ways are there? Definitely there is only single way. 1th coin onwards, there is only single way, that you choose 2 plus 2, and that is it. So only one way is there. So I'll choose this one and I'll return the sum of these two values, 0 comma 4. So I'll return 3, and definitely whatever sum gets returned from here, that will be, I think, only one possible way to actually create only 5 only, right? And this is the recursion tree for this problem itself. I hope this is clear to everybody, and I hope recursion part is clear to everybody. Let me write the recursion pseudocode itself, then we'll move to recursive code. So let us write the recursive pseudocode for this. So function recur, I'll name it recur only. That's what we are doing in this series. I'll pass what parameters do I need? I'll need the coins array, I'll need the ith index I'm standing on, and I'll need the amount, right? These are all the things I need, right? Now you can see all this stuff here, and what I want to do, I'll not write the base cases first. Let's just complete the recursion body. If we are standing on some index, what calls are we making? If we are not on a base case, of course, yeah, first call is if I stay. Number of ways to achieve a particular sum if I stay on the same coin. That is, I'll call the recur again, and coins array I'll pass as it is, I'll pass as it is, amount will be what? Amount minus the ith coins of I. Is this clear to everybody? Yes or no? Let me move this a little bit to a side. This is actually confusing everybody. So okay, I'll make this recursion call. If I move to the next coin, move to next, and never look at this coin again back in the future. Recur for coins I plus 1. I'm not choosing any coin. I'm just moving to the next coin. So amount will be as it is. AMT. Amount will be as it is. In the end, I'll return what? Return stay plus move to next. And this is the sum I'll be returning. Let's talk about the base cases itself. If you're talking about the base cases, if what? If coins, if amount becomes negative, I'll return what? Zero ways. If amount becomes, if let's say not amount, let's say I, index I is what? And before this negative case as well, I wanted to handle another case. If the amount becomes zero, what do we return? I return a 1. That I have found a single way. If amount becomes less than 0, return 0. If what? If ith index is equal to coins dot length, I'll simply return what? 0. That, if amount is not 0, if it is not less than 0 as well, this means that we are having a positive amount. And still we are having a positive amount and we are having no more coins left. This means that there is no way possible. I'll return 0 from itself. This is the recursive pseudocode itself. Let us try to convert this into code itself, and then we'll move to the memoization of this problem. So here we are in the code editor itself, and what we have to do, I'll simply write a recursion function, public int recur, integer array coins. This is what I need. Integer amount, integer I index on which the coin I'm looking at, integer amount which is remaining. AMT, I'll write it because that's what we have been following. So this is the recursion parameters, and let's write the body first. I'll write the base case in the end. If I stay on the same coin, recur for coins array, I will be remaining the same because I'm standing on the same coin. Amount will be what? Minus coins of I. Integer what? If I move to the next coin, is equal to recur for coins I plus 1, and amount I'll pass as it is because I'm not choosing any coin. I'm moving to the next coin. In the end, I'll return what? The number of ways you can make the sum equal to 0 by moving or staying. Making the desired amount. Now for the base cases, if amount in some day in future, if amount becomes equal to 0, I'll return that I found a way. I'll return a 1. If someday amount becomes less than 0, I'll return a 0. If someday amount becomes what? If I becomes equal to coins dot length, I'll return 0 as well. That still the amount is positive and I is become negative. So what's the point? I is equal to coins dot length. What's the point? I'll return what? Return recur for coins. I'll pass initially. I'll pass the 0th index. I'll pass the amount here. And now let us try to run this code itself and let's see if it is working. Spelling is mistaken. It is getting accepted. So this is the recursion code. Let us quickly convert into memoization itself. Now for converting this code to memoization, I'll simply copy this as what we are going to do. This is the trick. I'll write here wherever recur is there, I'll write memo. I'll pass a DP array as well, and it will be a 2D array because 2 parameters are getting changed. Yes or no? 2 parameters are getting changed. So DP array I'll take. And what I'm going to do here, the only thing which is remaining is here also I'll write DP. I'll write a DP here. And the only thing which is remaining is recall and remember. So if DP of I comma AMT is not equal to -1, I'll treat -1 as the state stating that I have not visited this particular index. If it is not equal to -1, this means that we have altered this index. This means we have already visited this index. I will return DP of I comma AMT. And what do I have to do? DP of I comma AMT is equal to, I'll remember it as well. Recall and remember, this is what we are going to do. Let's create the DP array itself, integer array. DP is equal to new integer. First parameter will be like I am writing here, right? So definitely I is bound by the coins dot length array. So I'll write here coins dot length. And the second parameter is definitely the amount I'm trying to access. So amount plus 1 because amountth index is also what I want. The only thing which is remaining is every person in this DP, I want to make them -1. So for in you can say integer I is equal to 0, I less than dp dot length I plus plus arrays dot fill dp of ith array you have to fill with -1 because this is 2D array, so this is definitely the 1D array inside this 2D array. I'll pass here, let me know, copy paste this call dp, I'll pass here and I'll do what, I'll pass, yes, I'll rename it as memo. Rename it as memo, and I think that this is it for the this Memoisation code itself. Let's try to run this code and then let's see if this code is working at all. It is getting accepted. Let's try to submit this code. Let's see if it is working in the submission. Yes, it is getting submitted as well. Let us quickly convert this to tabulation itself. So apparently before starting the part for recording the tabulation part of this problem, I forgot to press the record button. So here I am going to explain that again. So no worries. I'll quickly explain that. Right. So public, you have to convert this code for tabulation. So public int tabulation is the function. Integer coins and integer amount, that is what I have to pass here. And integer 2D array dp is what I'm going to pass here. Right. So tabulation is done. One thing we have to remember is that we have to start from the base cases, and you can definitely see here the base cases are I going to cost length, coins length, right? I starting from 0 and trying to go to coins length, and amount coming to 0, right? These are the two base cases we have to start the loop from, because in tabulation, we start the loop from the base case itself, correct? So let us quickly write the tabulation code for this. So I'll start my first loop for integer I, which will be starting from which index? It will start from coins.length -1, because we have to start from base case in tabulation. Coins.length -1. I greater than equal to 0, I minus minus. Another loop I need because the DP is of 2 dimensions, and the second loop will start from where? I'll take a variable instead of j, I'll take AMT variable. For integer AMT is equal to, it will start from where? It will start from, you can see the base case is having 0. So amount will start from 0. Amount will go all the way up to this amount variable itself, AMT plus plus. So these are the two things I'm having, and simply after this step, I simply copy paste this code. This is the code which I've copy pasted. Let me remove the recall statement from DP. I'll remove this recall statement. Let me remove this recall statement from here. Let me remove this statement as well, remember statement as well, right? I'll simply remove these two things. Now what do I have to do? This is the trick we are talking about, and if you don't know what trick I'm talking about here, to convert memoization code to tabulation code, you can definitely check out my first lecture, which is on Fibonacci series. I'm not telling you to watch the whole playlist in order to understand this trick. You can simply watch my Fibonacci series lecture and you will get to know the trick we are using to convert a memoization code to tabulation itself, right? And for those who already know, we already know that now it's time to replace the return statements with continue statements, continue and remember. So amount is equal to 0. We have to remember and continue. So I'm returning 1, right? So I'll do what? dp of I comma amt is equal to 1 and then continue. I'm remembering the answer for amt is equal to 0 and then I'm continuing. Here, definitely less than 0, this will never go. I will never be equal to coins.length, so I can simply remove this statement as well. Now I have removed all the return statements. That this is the time where I replace all the memoization calls. So instead of this memoization call, I'll do what? I'll try to access DP array. So DP of something something. So I will be as it is, you can see, but j will be what? AMT minus coins of I, correct? This will be the j, you can say the second parameter of this, right? So this exact parameters we take here, you can definitely see. I'll try to access DP of I plus 1 and AMT I'll pass as it is, right? Because here also as parameters you can say I'm passing I plus 1 and AMT. So definitely I'll remove this statement from here and stay and move are done. One case is remaining. Here can you see sometimes it is possible that amount can go less than 0 as well. So just like in previous questions, I'll simply add a ternary operator here. AMT minus coins of I greater than equal to 0. If this is greater than equal to 0, then only try to access this thing, else try to access this particular thing. So I'll simply write here a 0, right? And here also I can definitely go out of bounds, right? So what do I have to do here? If I plus 1 is less than coins.length, then only I do this, else I simply make it 0, right? So this is the thing I want, and I'll simply return what? I've simply return 0 comma amount from here, because this is what I'm doing in recursion call itself. So whatever we call for recursion, that DP index be returned 0 comma amount, I'll return from here. And this is the whole code which is converted into tabulation itself. You have successfully converted the tabulation code, memoization code to tabulation itself. Let me call this function. So I'll call return tabulation. I'll pass here the coins array. I'll pass the amount, coins array, amount, and DP array. Right. I'll pass these as it is. I think it is okay. Let's try to run this code now. All right. Okay, so it's running fine. Let's try to submit this. And this is the tabulation code itself, right? So definitely this code is working fine. So let us see the space optimization for this problem and let's move forward. So now we're going to look at the space optimization which is getting implemented in tabulation itself. And earlier we were using a space of n cross amount. Right now I'm only taking a space of O of amount, right? So I've created this array, right? And at every index I'll store that what are the number of ways to form that particular amount, correct? So in how many ways, but initially what I'll fill that in how many ways can I simply make a zero? There is a single way to make a zero. Select nothing. You'll be getting a sum of zero. So there is one way to make a sum of zero possible, and I'll denote this way as choosing dot. Dot means choosing nothing. Okay. All right. So I'll iterate coin by coin, because remember what we were trying to do in recursion. I was trying to get the result using a single coin, and then I'll move to the next coin. So what I'll do here, I'll look at all the possible results for a single coin, and then I'll try to choose the next coin after that coin. If it is not clear, don't worry. We'll be doing it. No, like it's like easy. Full focus. Look at this coin one. If I'm allowed to use coin one and I want to make a amount of one, is there a possible way to make this amount? If amount is 1 and I use coin 1, the remaining amount is 1 minus 1, which is 0. In how many ways can I make 0? There is one way, which is dot. So how many ways I can make 1 possible? It is this dot. After this dot, if I add a 1, right, this is possible, right? If I add this 1, it is possible, correct? I have chosen a coin 1 and it is possible to make a sum of 1. There is one way I have found to make a 1. Okay. One way I have found to make a 1. All right. Let us look at this 2. How many ways can I form a 2 if I'm choosing 1 right now? If I'm choosing 1 right now, remaining sum is 1. And in how many ways can I make 1? This is a single way to make 1. So whatever is there, I'll add here. What I'll do, I have found a 1 way to make 2, which is whatever is this 0, 1. I'm choosing 1 again right now to make some 2. So I'll add a 1 here. In front of all these people, I'll add a 1. Okay. Don't worry, it will get clear. So let's try to make 3. If I'm choosing 1 right now and I want to make a sum of 3, remaining sum is 2, and in how many ways can I make 2? This is a way to make 2. So I'll make the sum of 2 and then I'll choose 1. This will be making a sum of 3. Simply saying that I am having a single way to make a 3 as well. Okay. Let us go here. 4 is here. Now for this 4, what I'll do, if I choose 1 right now, if I'll choose 1, don't worry, by the time we reach 5, it will be clear. If I choose 1 right now, I'll be left with the sum of 3. And this is the way I can make a sum of 3. So I'll make the sum of 3. I'll make the sum of 3. And what will I do? I will add a 1 in front of it, because this is a coin I'm choosing right now. And I found a single way to make a sum of 4. If I want to make a sum of 5, the remaining sum will be 5 minus 1, because I'm choosing a coin of 1. These are the ways I can make the sum of 4. I'll make the sum of 4 and I'll choose 1, like I'm like choosing the coin 1. So this 1 is added in front of this thing, and I found a single way to make a sum of 5 as well, right? Now in these all things, we have chosen all the possibilities of 1. I'll not look at this 1 back again. I'll look at this 2 now, because if I look at this 1 back again, I'll be forming permutations, right? So I'll just look at this 2 now. Look at this 2 now. You have to focus on this 2. Using this 2, I'll iterate this whole array. I start iteration from 1 only. So if I'm standing on 1th index, if I want to make an amount of 1, these are the amount. These indexes are representing the amounts. If I want to make the amount of 1, and I am allowed to choose a coin of 2, the remaining amount is 1 minus 2, which is minus 1. Invalid index, nothing will be added, my friend. Nothing will be added. Let us try to make add, the number of ways if I am allowed to choose 2. So if I am allowed to choose 2, the remaining sum will be 0. And how many ways are there to make 0? It is a dot. So what will I do? Dot is the number of ways to make a 0 and 2 is the coin I'm choosing right now. So this is another way I found. This thing will be added here. So whatever are the number of ways to make 0, that will get added here, because that is actually leading to the target cell, which is of 2. Okay. Look at this 3. I want to make a sum of 3. In how many ways can I make a sum of 3? So if I am allowed to choose a coin of 2, if I choose 2, remaining sum is 1. How many ways I can make 1? Only one way. And these are the number of ways to make 3 as well. Just look at these ways. I'll write these ways here. And since I'm allowed to use 2, I'll use 2, this coin 2 here. So this 1 will be added to this index. So what I'll simply do, I'll simply make it 2. Look at this 4. Look at this 4. Now for this 4, what are we supposed to do? Here I want to choose a coin of 2. And if I choose a coin of 2, remaining sum is 2. How many ways can I make 2? I can make a 2 using this way, or I can make a 2 using this way. In front of both of these two ways, if I choose a coin of 2, can I say I'll be forming a sum of 4? Yes. So whatever is this number, I'll add it here. So this will become what? It will simply become 3. Look at this 5. Look at this 5. In how many ways can I make a sum of 5? Using, if I'm allowed to choose a coin of 2. If I choose a coin 2 here, the remaining sum will be 3. And these are the ways to make a sum of 3. So let's write the ways to make a sum of 3. 1, 1, 1 and 1, 2. These are making 3. And if I'm allowed to choose 2 right now, I'll add 2 in front of these, and these are forming 5 itself. And whatever number is written here, I'll add here, and it will simply become 3 here as well. Correct? So this is all the possible things if I'm only choosing 1 and 2. Let's try to choose 5 right now and not look at the previous indexes, because they will give me permutations. I only want combinations. So I look at this 5. So when we are looking at this 5, I'll start iteration from 1. If I'm choosing 5 right now, the remaining sum will be 1 minus 5, which is negative, so nothing will be added. 2 minus 5 will be negative, nothing will be added. If I want to make a sum of 3 and I'm choosing coin of 5, 3 minus 5 is negative, nothing will be added. 4 minus 5 will be also negative, nothing will be added. 5 minus 5. If I'm allowed to choose a coin of 5, remaining sum will be 0. In how many ways can I make 0? There is one way, choose nothing. So I'll make this way, and I'll add a 5 in front of this way, because I've chosen this 5. I'm choosing this coin 5 only. Similarly to saying that whatever is written here, I'll add here, right? The number of ways I can make the remaining sum is the number of ways I'll add that to this sum itself. So this becomes 4, and this is the iteration complete. There are no more people and no more coins are left. So you can see on this index, to make a sum of 5 using these coins, you can have 4 different combinations. And I hope this space optimization is clear to everybody. Let us look at the code of this thing itself, and then we'll wind up the video. So we are in the code itself, and let us write the space optimization code. I'll create a separate function for this. I'll write here public integer space optimization. I'll write here integer array coins, and I'll pass here amount. Space optimization is done in 1D DP itself. So integer DP is equal to new integer. Amount is what I want. Amount plus 1, right? Initially, I'll fill whatever I know. So amount DP of 0 is, of course, I'm having one way to create 0. So that's I'm taking, right? Now for every coin, I have to iterate the whole DP array. So for what I'll do here, for integer coin in coins, what I'll do, I'll simply say I'll traverse for every, you can say, amount. So I is equal to, I'll write amount here. Amount is equal to 1. AMT less than equal to amount AMT plus plus. Correct. You can use I or J here, but I'm using AMT because that is getting related to that above thing itself. So if I want to make this amount integer, and if I want to make this particular amount and I'm using this coin, so remaining amount rem AMT is what? It is simply, I'll simply write AM amount is what? AMT minus the coin I'm using. It is possible that remaining amount can be less than 0. In that case, I'll simply continue. Nothing will be added. Negative. And if that is not less than 0, if it's greater than equal to 0, this means that that index exists. What I'll do? DP of what? AMT plus equal to DP of rem amount. number of ways I'm able to make the remaining amount, I'll just add that coin in front of all these ways and I'll add to this amount itself, and that will be the result of this thing. In the end, I'll simply return what? I'll simply return DP of amount, and that will be the thing. So yes, I think we have done coding. Let me show you the board itself. So here you can see that, if we are trying to make 5, negative, remaining amount is what? 3 minus the coin we are choosing, it is negative. So whenever it's negative, I'll simply continue, I'll add nothing. And if let's say I want to make a sum of 5, how many ways are there to make a sum of the remaining amount? 0. It is a single way. So I'll write all these ways here, and in front of all these ways I'll write a 5, and basically adding this count to this particular thing, right? So I hope this is clear to everybody. Let us quickly call this function of space optimization. I'll comment everything and I'll return what? Space optimization. I'll pass here coins, I'll pass here amount. Okay. I think it is clear. Yes, coins and amount. Let us run this code itself and let's see if it is working. Let's submit this. It is working just fine. And yes, so these are all the approaches to this problem. I don't want to miss any of the approaches. The videos might be coming a little bit long, but yes, I don't want to miss any approach we are doing. So talking about the time complexity, here you can definitely see that, this particular thing we are having, recursion code. Recursion code is a little bit peculiar when you want to calculate a time complexity. So the time complexity, I'll tell you a simple trick for this as well. How many calls are you doing? 2 calls, and at most, what will be the depth of that recursive tree? Look at this recursion tree. We drew a recursion tree here, right? So this recursion tree, what is the deepest place for this recursion tree? Can you see, if I only choose this coin 1, if I keep on choosing this coin 1, right, that, but like using the coin 1 itself, that would be the deepest state of this tree, right? In the worst case, let's say I'm having a coin 1 and let's say the sum is very big. So can I simply say that the deepest node will be the sum of that tree, right? The amount I want to achieve. So basically 2 calls I'm making, and the deepest call would be the, like, due to this amount variable, I can go as deep as possible, right? And if the coin is 1 steps, the tree will become very deep, right? So the time complexity for recursion code is simply the amount of calls you're making raised to the power to the depth, whatever depth you are going. So it is 2 raised power the amount, correct? For this time complexity, of course, memoization is reducing it to n square itself, right? And you can definitely see we are trying to access I comma j every time, and that if we get an I comma j, I return. This code is definitely n square because you can simply see 2 loops here. This code is linear. This code is n square time, but the space complexity is what? The space complexity is O of amount. O of amount. Here the space complexity is, of course, O of n into amount. N is coins dot length, right? In memoization as well, right? So definitely, I hope this is clear to everybody. This problem is clear to everybody, right? Don't forget to, don't forget that research I was talking about in the starting of this video, and I hope you are loving these videos. I am trying to cover as much as possible, as deep as possible, so that, I'm trying to ensure that if you have done this DP course, there is nothing else you want to watch for DP, right? So videos might be becoming a little bit longer, but I hope you're enjoying this time you're spending with me through this video. So yeah, so let us end this lecture itself, and yeah, I hope you're enjoying the lectures. Until the next video drops.